Okay, we've got a three-part inverse trig question. Part A is the trickiest of the three parts, and is this, right? We want to show that that expression there on the left is equal to 2x squared minus 1. And they've given us for the range of -1 through to 1 for x values. That domain there is pretty typical for anything involving inverse, because if you remember back to our inverse graphs, inverse sine, it just rotates. It only exists for x values between -1 and 1. So whenever you're dealing with, equations or expressions involving inverse trig, it's pretty normal for them to restrict the domain to just -1 and x, for the obvious reason that at least the inverse function actually exists within that range. All right, so we need to prove this identity here. Just to give you a heads up of what's happening afterwards, part B is asking us to show that this relationship here is true, which ultimately we're just gonna, we're gonna use the part A result for that. And likewise, part C gets us to solve an actual inverse trig equation. Looks pretty tricky here on the surface, but by the time we've done A and B, part C will actually probably end up being the easiest of all three parts. Okay, so let's get into solving part A. So yep, we've got orange, we're good to go. All right, so we want to show this result here. Okay, so just firstly, what I'm going to do is like inverse sine, we've got inverse cos, they're both going to be angles, right? So I'm just going to start off by just letting some angle equal inverse sine. Of course, that's going to imply that if theta is equal to inverse sine x, then taking sine to the other side. All right, we now know what x is equal to. X is going to be sine theta. Okay, so if that's what sine is, this is going to imply that inverse cos, right? Remembering they're complementary, sine and cos are complementary, like, cos 30 is equal to sine 60, cos 40 is equal to sine 50. They're complementary. So inverse cos will just be equal to 90 degrees, or in other words, pi on 2, minus theta, or the inverse sine x. So we've got an expression for inverse sine, that's going to be theta, and we have an expression for inverse cos x, that's going to be pi on 2 minus theta. So now we've got expressions for both of our inverse trig components. We can now properly look at this left-hand side. Okay, so the left-hand side is sine of inverse sine x minus inverse cos x, that's the left-hand side. And all we're going to do is substitute our expressions for inverse sine and inverse cos. Okay, so we sub them in, simplify it down. We end up with, theta, the two negatives, you're going to end up with two lots of theta in the end, and minus a pi on 2. Or in other words, I'm keeping in my mind that's 90 degrees, right? So we've got sine of some angle minus some other angle. We know a result for that. Sine of the first angle, cos of the second angle, minus sine of the second angle, times cos of the first angle. You'll notice that over here we have cos 90, which ends up equaling 0, right? Remembering our cos graph starts at 1, heads down to 0. So cos 90 is 0. So this whole term is just going to go away. Sine 90, I'm now looking at this term here. Sine 90, thinking of the graph, right? 90 degrees is equal to 1. So that's equal to 1. So ultimately, the first term just becomes 0. So you're going to end up with a minus 1 times cos 2 theta. So you just end up with minus cos 2 theta. Okay, from here, cos 2 theta is cos squared theta minus sine squared theta, but the whole thing's been minused, so I've got the signs there swapping around. And check it out, what is sine squared theta? Well, we know sine theta is equal to x. So we have minus cos squared theta plus x squared. What are we trying to get this to look like? We're trying to get 2x squared minus 1. There's no cos theta in the result we're trying to get on the right-hand side. And we know what sine theta is equal to, right? Right. So all we have to do is, we know cos squared theta would just be 1 minus sine squared theta. We've got this x squared here. And now we can replace our sine theta with x. And you end up with 2x squared minus 1, which is equal to the right-hand side as required. Okay, so there it is. So part A is done. And like I'm saying, this was the trickiest of the three parts. It was a result of, okay, well, we've got an angle here, let it be theta. And then once we have the inverse sine, we worked out an expression for the inverse cos, plugged them into the left-hand side, and just simplified it down. And eventually we ended up with the right-hand side. So I guess it was quite long, but there wasn't any one particular step that was super crazy hard or anything. All right, on to part B. So provided, x is between minus 1 and 1, which is actually what we want, right? Because we're dealing with inverse trig components. We want to, show this. Okay, so we can ultimately see that 2x squared minus 1. So we want to show that 2x squared minus 1 is between minus 1 and 1. Well, if we look back over here, what was 2x squared minus 1? It was this sine of this whole big, inverse sine x minus inverse cos x. All right, I'm going to we know inverse sine is an angle, inverse cos is an angle. So if you've got inverse sine x minus inverse cos x, it's just going to be some type of angle. One angle minus another angle is some new angle. So what I'm going to do is I'm just going to let some random angle, I could have used theta, but I'm going to use alpha now, because we've sort of used theta to mean something else different. I'm going to let alpha be inverse cos x, our first angle, minus inverse cos x, our second angle. Right, so alpha is some type of angle. Now we know from the sine graph, right, sine oscillates between, if you just have a regular good old-fashioned sine graph, what does sine oscillate between? 1 and minus 1. We know that if you have sine of some angle, any angle really, it'll always be somewhere between minus 1 and 1. And of course, I'm including the equals because it does actually reach and equal minus 1 and 1 on occasion. So what I've done here is, this is kind of really the official start of the proof. We know that sine of any angle will be between minus 1 and 1. And we know that inverse sine x minus inverse cos x is some type of angle. So therefore, I'm just going to sub that in. Sine of this angle here will also be between minus 1 and 1. As simple as that. Sine of anything will be somewhere between minus 1 and 1. The graph doesn't magically go above it, not unless you start adding, subtracting, or times in the graph. But if you just got a sine graph of some angle, it'll always be between minus 1 and 1. That's actually the proof. So it really was just the arrow, and then just subbing in, this interesting looking angle into sine, and there you've got it. So that's part B. Part C is probably the funnest, and yeah, truthfully, probably the easiest, to be honest. All right, so we want to solve this equation here. All right, first up, inverse sine x minus inverse cos x. It looks a whole lot like the result we got in part A. The only difference is it had a sign in front of it, right? It had been signed. Well, if you check the right-hand side, we have an inverse sign here. The very first step in my equation solving is I'm going to take this inverse sign and move it to the other side. Or you could like sign both sides, and the sign and the inverse sign would cancel on the right, and we'll leave you with the sign of inverse sine x minus inverse cos x is equal to 5x minus 4. But from my memory, I think most of you preferred the idea or the concept of just moving the inverse sign to the other side where it becomes the opposite. In other words, just a normal sign. Okay, so I've taken the sign to the other side. And now from part A, right, using results from part A gives, well, this whole thing was just 2x squared minus 1, right? And now you've got yourself a stock standard quadratic equation with the one provisor that, you know, that whole result from part A was subject to that domain, right? So our x values have to be between minus 1 and 1. So you know how to solve your quadratic equations. You're going to move everything across to the one side. All right, you've ended up with, oh, check it out, it's a trinomial. Factorize it any way you like, lots of different methods. Once you factorize it, you should have ended up getting as your two factors this, giving you results for x of, therefore x would be minus a half, or x could be equal to positive 3. However, we know we do have a restriction domain, so we actually have to reject that one there because it was not within the domain of minus 1 to 1. So hence, thusly, whatever you want to say, thus our solution for this equation here is minus a half. All right, hopefully that helped, and best of luck with your maths. I'll see you next time.